Good morning. This is Dr. Padgett. Today is March 2nd, 2021. This is Weather and Climate, Spring Semester 2021. Today, we are going to focus upon extreme weather. And so I'm going to share my screen. And so we are at week 6. And today's lecture focuses upon um, tornadoes, thunderstorms, and lightning. And so there's several resources here for us to look at. Let's look at thunderstorms first and their distribution across the United States, because of course thunderstorms are closely associated with tornadoes, especially when we have cold fronts during this time of year colliding with warmer, moister air. It's the perfect formula for the development of tornadoes. And so February is a month that is a high risk month for tornadoes, and also into March uh, around this time of year. So if you remember, just a year ago, a tornado tore through Nashville, went right through our campus. Here are some of the images, some of the damage that was done by that tornado just a year ago. 2 people lost their lives in East Nashville that evening. The tornado ranged from an EF3 on the Fujita Scale up to an EF4 during a period of time in Cookeville and Crossville, Tennessee, in that area. And so several people unfortunately lost their lives during that event. As you can see, there was a lot of damage. Some of this damage, there were buildings that were completely destroyed. It's a very powerful force, a very concentrated low pressure system. And so that tornado struck exactly a year ago today. But before we get into the physics of tornadoes, I just wanted to just mention that since we were directly affected by that type of storm last year, the origins of tornadoes, of course, thunderstorms. And as you can see, thunderstorms are not evenly distributed across North America. Obviously, if you can see the purple and red color area symbol in Florida and along the Gulf Coast region, um, notice that that's where we see the most thunderstorm activity. In Florida, those storms are mostly convectional thunderstorms. And so convection, remember, is when air rises um, or moves vertically through the atmosphere. What happens in Florida is the temperatures are relatively warm. Florida is a peninsula. It's surrounded on 3 sides by water. That air rises, it's very moist, reaches its dew point, and you get very frequent thunderstorms. And in some cases, those storms happen at about the same time every day, literally, in Florida. And so, but as we move out of the southeastern portion of the United States towards the west, you notice when we get along the west coast, very few thunderstorms, very few. Now it does rain, but they just don't get the violent storms as often as we do, almost 0 to 10 days per year. So there are people who live in Oregon, California, different parts, who have never experienced a thunderstorm in their entire lives. I'll give you an example. When I was much younger, when I was growing up in Baltimore, Maryland, some of my friends had cousins visiting from out of town from Sacramento, California. And we were playing ball, playing in the street, typical summer day. Um, Started to see the sky get a little dark. Then there was a flash of lightning, and then boom, 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 thunder. Typical summer day. The kids from Sacramento were scared to death. One of them just started running up the street. Another one ran into the house and got into a closet. One tried to crawl underneath the car. They were scared to death. We were 15 or 16 years old, but these kids, they had never seen a thunderstorm in their lives. They lived out here in Sacramento, California, and you can imagine um, if something like that happened, that that we take for granted thunderstorms, and we live in an area or part of the country where thunderstorms are frequent. We just take it for granted. I mean, they happen. It's just part of life. But if you're a teenager and you've never seen that before, it can be quite frightening to see the sky go black and you hear this, to see this flash of light come across the sky and then a loud boom, boom. You probably think the world's coming to an end, right? Uh, Now, on a more serious uh, level, there is an actual condition called astrophobia. And so, astrophobia is extreme fear of thunder and lightning. I mean, people can actually be diagnosed with astrophobia, clinically diagnosed, to the point that perhaps if they are unable to go to work after a long night of thunderstorms because they're so traumatized, they might perhaps be able to use their sick leave. So there is actually a medical slash psychological condition called astrophobia where people are uh, definitely psychologically impacted by these types of storms. I mean, imagine someone who might have grown up all his or her life in Los Angeles and then gets transferred to Atlanta or Orlando by their employer. They might have a difficult time adjusting uh, to the frequency of the thunderstorms. So, obviously, we can't talk about thunder without lightning. And so we have thunder and then we have lightning. And so the lightning frequency map, as you can see, closely follows the thunderstorm frequency map, with Florida being the clear hotspot. Lots of lightning in Florida, lots of lightning injuries and deaths in Florida. And so lightning is hotter than the surface of the sun. Bolt of lightning is 50,000 degrees Fahrenheit. 50,000 degrees Fahrenheit. Not a whole lot of people survive being struck by lightning for obvious reasons. And so, what happens with lightning? What causes the lightning? Well, it's really caused by an imbalance of charges in the atmosphere, and nature wants balance. And so, when those charges, positive and negative charges, are out of balance, nature quickly tries to bring that imbalance into balance by joining those negative and positive charges. And that's really a simple explanation or for lightning. It's a lot more complex than that. I'm just trying to get you to understand the basics of lightning. Lightning can travel quite far. Uh, Lightning can travel 10 miles and still be deadly. Uh, that's why at a football game or at a soccer game or at a baseball game uh, or at a golf match, if there's the presence of lightning detected, 10 miles away, that's when they start to clear people out of the stadium, get people off the golf course. Because what happens if they don't, here's an example of what happens when people don't heed warnings. So a couple of years ago on the let me see. Yeah, this happened a couple of years ago in Atlanta. Lightning strike. But these are some very lucky people. They were just injured by this lightning strike. So it was during a PGA Tour, Pro Golfers Association Tour Championship in Atlanta, which is right in the heart of lightning country. And the fans made a common mistake. What happens a lot is that, people don't heed warnings. So again, the PGA made the right call. The PGA actually has meteorologists that work for them. And there are meteorologists that work specifically for the Professional Golf Association for just this reason. So the PGA rightfully told people to clear the course. Obviously, not everybody's going to listen. So people, as you can see, went and stood underneath a tree or stood around trees. Now, unlike that, I don't want to call it a fairy tale, but unlike that misinformation, a lot of people have been told that lightning never strikes twice in the same place. That is absolutely false. Lightning repeatedly strikes in the same place twice because lightning is attracted to the highest object in any given area. Okay, so lightning is attracted to the highest or tallest object in any given area. And so if that happens to be a tree, lightning is going to repeatedly hit that tree. If it happens to be a lamppost or anything that's tall, a building, a church steeple, lightning is going to repeatedly hit that. So these people made a mistake that a lot of people make. It starts raining. You go stand under a tree to avoid the rain. Lightning hits the tree, hits the people, and they end up, in this case, being injured. But they're very lucky that they were not killed. A lot of people do not survive lightning strikes. So in terms of lightning safety, shouldn't be around tall structures or objects. You should not stand beside your car. Now, if you're inside of your car, the windows rolled up, you're okay. But if you're standing around this any metal object during a lightning storm, that's not a very good idea. Indoors, you should not shower during a thunderstorm. And there have been cases where the lightning has come through pipes and struck people being conducted. Water is an excellent conductor of electricity. Also, so those are the various lightning safety rules. And again, if there's a warning, just take cover. Don't think that just because the sky is clear that you can't be struck by lightning. It can travel many, many miles. Also, if you see a stroke of lightning and then several moments later you hear thunder, you might ask yourself, well, how far away was the lightning? Am I in imminent danger, or is it far enough away that I can be, assume some level of safety? Now, sound travels at about 1,000 feet per second, approximately 1,000 feet per second. That's the speed of sound. Now, we know that a mile is 5,280 feet. So if you're out somewhere golfing and you see a stroke of lightning, lightning always comes before thunder. Okay. So remember, a bolt of lightning is 50,000 degrees Fahrenheit. So if the atmosphere is 70 degrees Fahrenheit and it's suddenly heated to 50,000 degrees Fahrenheit, that gas or those atmospheric gases are going to expand. But really, if we go from 70 degrees Fahrenheit or 80 degrees Fahrenheit to 50,000 degrees Fahrenheit in an instant, that's not just going to be an expansion, that's going to be an explosion. So thunder is the explosion that occurs after the Earth's atmosphere has been rapidly heated up to 50,000 degrees Fahrenheit. It's literally an explosion. Now, the sound as it travels through the atmosphere travels at about 1,000 feet per second. So if you see a stroke of lightning and then you count 1 1,000, 2 1,000, 3 1,000, 4 1,000, 5 1,000, boom, thunder, that's 5,000 feet, or you're about a mile away from that stroke of lightning. If you count 1 1,000, 2 1,000, 3 1,000, boom, that's 3,000 feet or a little bit more than that. You're a little bit more than a half a mile away. That's kind of how you can gauge where you are. Now, if you see a stroke of lightning and bam, right afterwards, then you know that there's no distance between you and that lightning strike, and you really need to be concerned at that moment. That's a seriously dangerous situation to be in. So again, lightning, same basic pattern as thunderstorms. So thunderstorms and lightning are, of course, both indelibly connected to tornadoes. And so let's look at the tornado frequency in the United States in general. And so tornadoes, of course, follow the same basic pattern mostly as thunderstorms. But notice we have a concentration of tornado frequency here in the Great Plains region. That's also known as Tornado Alley. If you watch any of the tornado chaser shows, they're usually out here in Nebraska or Kansas or Oklahoma or somewhere in the Great Plains. Now, here in Tennessee, we might be led to believe, oh, look, we're in the very low, not as low as the West region, but the low frequency region for tornadoes. We might be under the false assumption or that we are, or we might hold the false assumption that we're safe. But we found out last year, of course, that is not the case at all. And in fact, if you take a look at this graphic, you'll see that Tennessee, Alabama, this part of the country, we're literally almost at the bullseye for what we call killer tornado alley. So even though there are more frequent tornadoes out on the Great Plains, you're statistically much more likely to be killed by a tornado here, right here. Why is that? Well, there are several reasons for that. A, if you've ever watched the tornado chaser show, you've probably seen a tornado going across a wheat field or a cornfield. Population density is relatively low in the Great Plains. And so in many cases, you could have a really good sized tornado not hit anything. Now, I have included a couple of cases. Moore, Oklahoma here, 2013 is an infamous case. Oh, wow. I'll have to fix that page. But the Moore, Oklahoma tornado is a infamous tornado, EF5, the most powerful type of storm that we can have or observe. And so so here's the Moore, Oklahoma tornado, about a mile wide. You can see, imagine that, a mile wide tornado. I believe it was an EF5, 200 mile per hour winds. Let's go back and take a look at the Fujita scale for tornadoes. That is the scale that we use to measure tornado strength. I'm gonna have to get back into the eLearn page here. Kind of skipped out of it. So here's the enhanced Fujita scales. This is how we measure tornado strength. So the tornado in Moore, Oklahoma, EF5, winds over 200 miles per hour, massive damage, almost just incredible structural damage and loss of human life. An EF4, 166 to 200 miles per hour, extreme damage, so on and so forth. The EF3 that came through Nashville last year, wind speeds of 136 to 165 miles per hour. Severe damage, as we saw, cars lifted off the ground. I think there was one, let me see. Yeah, this was a crazy, let's see, where is this image? Okay, here it is. So if you notice, here we had, this is from last year. If you notice, there's a car that was thrown into the third floor of this building here, which is just incredible. I mean, it's a small car, but still, that just shows you just how powerful these tornadoes can be. So that was an EF3, and it just launched that car up into the third floor of this building here. So you can see the kind of destruction that's associated with these different tornado scales. So the Fujita scale is what we use to measure the strength of tornadoes. So again, getting back to the high risk for tornadoes in this area, why the high frequency of, or relatively high frequency of deaths? As opposed to the low population density that we see in the Great Plains, we have relatively high population, or much higher population density in this area. Many more people live here. So if a tornado comes through Memphis or Nashville or Huntsville, Alabama, there are going to be people who are going to be impacted by that tornado. Also, if you look at the topography in the Tornado Alley area is very flat. So I'm sure you've watched some of the tornado chaser shows. They can be 4 and 5 miles away from the tornado and clearly see it. Here, it's very hilly, not easy to see a tornado coming. I have firsthand experience with that. So here we have, now this occurred in 1995, a good while ago, probably about 25 years ago. And at the time, I was teaching at Austin Peay State University in Clarksville. And I was on my way to work just like any other morning. And so I had to drive up Interstate 24, northwest on Interstate 24 to Clarksville. And as soon as I pulled onto the ramp from Raleigh Parkway on the 24, it was as if somebody threw a black blanket over my car. I mean, the odd thing about it wasn't really a cloudy day. It was it 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 really it really didn't look as if anything unusual was about to happen, you know. So my car just gets, there was zero visibility. It felt like my car was gonna get lifted up off the ground. Literally. I mean, I could just feel this force, and I heard this just loud noise. The wind was incredibly loud. Uh, so I made a mistake. I panicked. Yeah, I mean, a lot of us can say what we think we're gonna do in a given situation. If this happens, then I'll do this. But then when it actually happens, you don't know what you're gonna do. So here I am. I'm trained storm spotter. You know, I'm a trained storm spotter here, and I'm thinking I would know what to do in an emergency. But I panicked and I drove my car underneath the bridge, which was a mistake. That bridge, had that been a powerful enough tornado, that bridge could have collapsed right on top of me and my car. Fortunately, that didn't happen, but I panicked. What you should do if you're in a situation where you're in a car and a tornado is coming, you should get out of your car and get as low to the ground as you can. Even if you're in a ditch, you know, that will give you the greatest chance of survival, unless something falls on top of you. But really, your best chance of survival is to get low. I didn't. I panicked. I drove underneath that bridge. Um, that tornado continued toward the northeast and struck Rivergate Mall. A lot of you all probably know where Rivergate Mall is in Nashville. So this is a tornado that tore up Rivergate Mall. Now, what happened on this day was, you know, I went through that experience and went to work. And after I got to work, the local newspaper, the Nashville Banner, called me because I am an expert, and they wanted to know, what happened. What happened with this tornado? What are the processes? And so I did this interview. They did not know that I had actually been in the tornado earlier that day. It's a very odd coincidence. So yeah, I've seen these forces firsthand. And it's very, very scary to see that kind of a powerful force bearing down on you or around you. Um, and so part of the reason that I might not have seen that tornado was because this area is very hilly. It's easy for a tornado to hide behind a hill and come out from behind it. Um, Next, so we have high population density, um, hilly topography that can hide a tornado that results in more deaths. Also, there's an unusually high percentage of people who live in mobile homes uh, in this part of the country. If you're in a mobile home, you're in a lot of trouble when it comes to tornadoes. About half of the deaths that occur from tornadoes are people who live in mobile homes. People who live in mobile homes. So it's I don't know. It's a very tragic situation. If people are, they're in a mobile home and a tornado strikes, they really have a very significantly high chance of being severely injured or killed. Um, Now, the last factor that results in increased deaths in this area of the country is that, notice this is a leading area of the country in terms of nighttime tornadoes. So that's very dangerous. A tornado that comes along at night. And so a person could be asleep and basically never wake up, struck by a tornado. They happen very fast. Tornadoes can move as fast as 30 or 40 or 50 miles per hour. So there's no outrunning a tornado. And in some cases, even outdriving a tornado might be difficult or if impossible or put you at risk if that's your plan of escape is I'm going to drive away from this tornado. Maybe you're able to do that. Most likely you're not going to be able to do that. So let's look at some of the processes that occur inside of these storms very quickly. So, well, what happens with these thunderstorms? What is the physical process that occurs? So you can do that, see that in this slideshow. So first, of course, in some cases, we have some form of lifting, either through frontal lifting, lifting of air across a frontal boundary, or convectional lifting. Have updraft of air that occurs. That air reaches its dew point, or those gases in the atmosphere reach their dew point temperature. Condensation takes place, and we begin to see the formation of clouds and rain. And so we have various types of thunderstorms that form. Here is where we can see a line of thunderstorms here across western Florida, across Alabama and Georgia. And this red, that's a squall line. So that squall line is probably at a frontal boundary, most likely a cold front boundary. And here again is another thunderstorm frequency map. We talked about thunderstorms forming in Florida, and of course along frontal boundaries. And this is exactly what I was talking about earlier that happens around this time of year. We still have that CP, that's the continental polar air mass. And then we have the maritime tropical air mass here, which is a warm, moist versus cold air mass. The colder air forces the warmer air higher into the atmosphere. And then we have that frontal lifting and convection that occurs. Thunder and lightning, all the physical processes that occur in and around these storms. Hail. Hail is frozen precipitation that is associated with thunderstorms. And then there's the Fujita Scale and some other very important information to know about tornadoes and thunderstorms. But let's look at specifically the hail formation process. So we talked about different types of frozen precipitation. In this case, what happens is, of course, we have this uplifting or convectional forces forcing air high into the atmosphere within a cumulonimbus cloud. The water, rain, liquid water is pushed higher in the atmosphere, but where it gets cold enough to freeze. And depending upon how many times this ball of ice gets pushed up higher in the atmosphere, it gets bigger and bigger until finally it's able to fall to Earth in the form of hail. So hail is associated with convectional forces as opposed to, say, sleet. Sleet is also frozen precipitation, but it just falls to Earth in in frozen form or in solid form, uh, not associated necessarily with any type of thunderstorm. So clearly, the hail can occur in the middle of the summer. You can see there are places that can literally be coated um, with hailstones in the middle of July, August, May, if a thunderstorm or if a tornado occurs. And so hail and tornadoes are very closely associated with one another. So that's one thing that should there's a warning for us if we see or if and when we see um, hail associated with a thunderstorm. There's a great likelihood that um, there's going to be tornadic activity. Here's a graphic showing tornado frequency at various places in the US. In this article you might want to read. Here's a good graphic. So notice that um, February, March, April, May, across the Great Plains when we have the greatest frequency of tornadoes. And then here is the southeastern US. The pattern is not quite the same. Notice that in February we have this spike. In March we have another spike of tornadic activity here in the southeastern US. So this is where we have to be vigilant and pay close attention. Here's tornado frequency by size of tornado um, in various parts of the US. So what we're going to do on Thursday is I'm going to perhaps have you all have the opportunity to become trained storm spotters. Now, normally we would do the storm spotter training on campus live, and the local National Weather Service would come here, and after about a 2-hour session, you all would become storm spotters, and you get a card, or I don't know if they even give these cards out anymore. So what is a storm spotter? A storm spotter is a person who goes outside and reports what he or she sees during severe weather. And you might think, well, we have all this fancy radar. Why do we need to have people outside looking at tornadoes? Well, weather radar, let me see if I can. Yeah, so this is in today's news. Radar has blind spots. And so what happens as we get farther away from radar stations, radar waves get farther away from the surface of the earth. And so let me see if I can. So here is, say, a radar station, and here's the Earth. And notice as you get farther away from the radar station, uh, the farther away from the ground, the radar is able to detect what's happening on the Earth's surface. So here we have a tornado. Clearly, the radar is not detecting it, according to this graphic. And so we still need people on the ground, human beings, to spot tornadoes on the ground and then report those into um, local news stations. So um, add this to our materials. Really good graphic there. So that's what we're going to try to do on Thursday. I know that we did virtual tornado spotter training last spring, so we're going to try to do that again, so that you will become a certified storm spotter um, after completing that training. And so the next thing I want to do is to do our usual weather map interpretation. And so we'll go to the online weather resources, data stream page, and we want to see our Isobars front radar. So this is what's happening today. Notice that the radar, speaking of radar, is detecting quite a bit of upper level activity across the southeast. Clearly some storms and rain here. Notice that there is a stationary front here. This is a very interesting situation. So it appears as if this cold front has pushed south into the Gulf, and that has resulted in a wide area of precipitation. So this is typical of a warm front, uh, uh, a stationary front boundary, perhaps. And so we can clearly see the high pressure here, this kind of cool front coming down. Notice that the temperature at this time in Atlanta, 46 degrees Fahrenheit. So there are cooler temperatures, 44 degrees, 53 degrees Fahrenheit in Charleston, South Carolina. Little Rock, Arkansas, 41 degrees Fahrenheit, 42 degrees Fahrenheit in Nashville. So relatively cool air mass coming through this region at the time, encountering warmer air. Remember, it was much warmer just a few days ago. And now we see this clash of these air masses resulting in precipitation. High pressure in the Four Corners region, very low wind, high pressure, clear skies across the region here. On the West Coast, we see here being affected by a low pressure system, not much happening there. Here we have a warm front crossing the Great Plains, and it's really not a strong warm front. You notice that this is probably the continental tropical air mass. As you can see, the wind direction is southerly and southwesterly, which would be indicative of the continental tropical air mass. So let's say on the midterm exam, if I was to ask you what is likely to happen over the next few days at Minneapolis, Minnesota, Would temperatures get warmer? Will they get colder? Will they stay the same? Your obvious answer should be that these temperatures will get warmer because there's a warm front approaching Minneapolis right there. As far as, say, Little Rock, Arkansas, what's happening, what is going to happen? Well, there's probably some rain occurring. The sky is 100% completely overcast, and the barometric pressure is about 1,027 millibars. 1,027 millibars. It's like we only have 2 digits there. So you're gonna have to be able to predict what's going to happen in any place that we are looking at based upon what we're observing on these various weather maps. So I'm going to save this weather map, save yet another weather map. So this is the March 3rd weather map for you to take a look at. And so again, when we come back next time, we'll discuss in detail the results of the Hawaii lapse rates exercise that's due today in a few minutes. And we'll also perhaps do some virtual storm spotter training that will hopefully get you to become a certified spotter. I'll set that up for Thursday. And we might do a bit of a discussion about the article reviews. And of course, some form of preparation for the midterm exam. Let's see, the midterm exam is, midterm week is going to be next week is midterm week. So probably next Thursday, the midterm exam will be administered, and you see I've put a lot of the important midterm terminology and facts in the lectures for each week. So that is some of what will need to be known along with everything else for the midterm. Are there any questions at this time? You have any questions, Theodore?
No, please, I don't have any questions.
Okay, so I'm going to stop recording.